All right, folks, jumping right in. Last video was on mass stoichiometry, obviously dealing with masses of chemicals. This is gas stoichiometry, dealing with amounts of chemicals, but unfortunately for us, gases are highly variable, dependent on their pressure and temperature. So remember, if you heat a gas up, it wants to expand. If you cool a gas down, it wants to condense and take less space up. If you put pressure on a gas, you squish it, it takes up less space. If you have it under low pressure, it likes to expand to fill its container. So that means that pressure and temperature matter. So the only ways that we have learned, and they're actually the only ways, to convert between a combination of pressure and temperature and a number of moles is either going to be the ideal gas law or those two shortcuts we learned in Unit B. At STP, 1 mole of a gas, doesn't matter what it is as far as we are concerned, takes up 22.4 liters of space. And at SATP, 1 mole of gas takes up 24.8 liters of space. So when we go through these questions, we're going to use a combination of pressure and temperature and moles in order to find out volume. In other words, how much space a gas takes up. You may be asked to calculate something else, like if they give you volume, they might ask for pressure. They'll say, how much pressure does this gas exert? Well, you just use the ideal gas law, and instead of solving for volume, you solve for pressure. So you guys are pretty good at math. You've really shown that you're strong algebraically, so I'm not really too concerned about that. So we're going to be dealing with the straightforward ones first. I just want to get our brains warmed up. So calculate the volume occupied by 3.54 moles of hydrogen gas at 320 Kelvin and 125 kPa. So these are not either of these setups. So we need to use the ideal gas law. So we need to use PIV-NERT. PV equals nRT. Remember, P is for pressure, which we have. V is for volume, which we're trying to solve. N is number of moles of gas, which we have. R is a special number called the gas constant. And T is the temperature in Kelvin, which we got. So we need to rearrange this formula in order to get volume all by itself. And it does not take rocket science to figure that out. We divide both sides by pressure. That's going to get rid of pressure on one side, giving us V equals nRT divided by P. So my N is number of moles, 3.54 moles. R, I'm going to write R as a fraction because it really is. It's 8.314. And the units, yes, I'm going to ask you to do the units. kPa liters divided by mole Kelvin. Yeah, it's awkward and weird, but you guys crushed that in gas laws, so I'm not too worried about that. Now we have to multiply by T. So multiply means put it on top of a fraction. So the temperature is 320 Kelvin, so 320.0K. Degrees Kelvin. And then we divide by the pressure, which means we put it on the bottom of a fraction. So 125.0 K, or kPa, kilopascals. So now we are allowed to do our unit crossing out. So we've got degrees Kelvin on bottom and top. They cancel. We've got kilopascals here. We've got kilopascals here. They cancel. We've got moles on the bottom, moles on the top. Bop, bop, those cancel. Hey, look, what's the only unit that is surviving here? It's liters. Unreal. What is the question asking us? Volume. How do we measure volume? In liters. So that's how we know that we did our question right. You should always be using your units, and you can't just fudge it and say, oh, well, yeah, Lorenz asked me for liters, so I'm just going to put liters. If you just put all of this stuff in here randomly and then you put liters at the end, there's no way of, unless you cross stuff out, there's no way of proving that you know what you're doing. So always put the numbers in and cross them out, or the units in, cross them out appropriately. Remember, we multiply all the numbers on top. So 3.54 multiplied by 8.314 multiplied by 320. We divide by the bottom numbers, which is simply going to be 125. And we only have 3 sig digs to spend, so we have 75.3 liters of hydrogen gas. So that's just getting us back in the saddle. Now we are going to get into one of these questions. I'm just going to change this to Kelvin, just so we can get rid of any conversions here. Okay, so 3.22 moles of ethane is combusted. What's the volume of CO2 that we form if the reaction conditions are 404 Kelvin and 115 kPa? All right, so we have to do stoichiometry. So we already have been given moles of our given, but we don't know our required. We got to write down a combustion reaction. So ethane is C2H6 gas. It combines with oxygen, O2 gas. The numbers in front, remember, we don't worry about until we balance it. And that's going to form two things. A combustion reaction forms carbon dioxide gas and H2O gas. Now we have to balance this reaction. Unfortunately for us, we are going to hit a snag because one thing that you can do is kind of a little cheat. Divide the number of hydrogens by 2. If it's an odd number, that means you have to double everything. So I'm going to double my ethane, and now I'm going to start going through from carbon to hydrogen to oxygen. You always go CHO. You do it in alphabetical order. So 2 C2H6s, that's 4 carbons. That means we make 4 carbon dioxides. 2 times 6, that's 12 hydrogens. 12 divided by 2 is 6. And now we figure out how many oxygens we have. We have 6 plus 8. That's 14. So that means we'll have 7 O2s. So here's our balanced chemical equation. So we have moles of ethane. So 3.22 mole of ethane. I'm going to throw it into our mole ratio. Remember, it's required carbon dioxide divided by given. It's going to give us moles of carbon dioxide. So 6.44 mole of CO2 gas. Then we need to turn moles of CO2 gas into a volume. How do we do that? We need a temperature, a pressure, and 8.314, which is our mole, our gas constant for moles to volumes. So we're still using V equals nRT divided by P. We can recycle that from before. I'm not going to go through the math to do that. This is how we turn a number of moles at a particular temperature and pressure into volume. So now all we have to do is throw that in. So my N is 6.44. So there's my N. That's moles. My R is that big honking number, 8.314. The number's not big, but it is in kilopascal liters over mole Kelvin. So that's an R. Then our T is up top, temperature 404 Kelvin. .0 K, and then 115.0 kilopascals is pressure, and that goes on the bottom. Why is it on the bottom of this fraction? A lot of folks see this and they're like, why are you putting the T and the P together? Because I can. This is the same thing as saying N times R times T divided by P. Literally the same thing. Why does that work? Math. Stuff that we know from other classes. So we go through, we cancel out what we can, moles and moles, degree Kelvin, kilopascals, kilopascals. Holy smokes, it's going to be liters of CO2. Beautiful. So now all we have to do is the math. So remember, we multiply by all the numbers on the top. So 6.44 times 8.314 times 404. Then we divide by 115. And we get 188 liters of carbon dioxide. So you burn 3.22 moles of ethane and you get 188 liters of carbon dioxide at 404 K and 115 kPa. Going to do one more reaction here. How many liters of hydrogen gas are needed to make 20 or 250 kilograms of ammonia? Here, I'm throwing a little bit of a monkey wrench into the whole thing. I'm giving you a mass. So 250 kilograms of ammonia. I know that ammonia is a gas, but let's turn the ammonia into moles, because remember, we can't go from grams to volumes. We need to go through moles. Everything goes through moles. So first of all, let's just do our little reaction. And our reaction is 3H2 plus N2 makes 2 NH3s. And I could have given you the, hydrogen gas and nitrogen gas combined to make ammonia. Since we've seen this reaction a number of times, it's not really that big of a deal to carry on with it. So we need to make 250 kilograms of ammonia. So what's the molar mass of ammonia? Well, it's NH3, so that's 14.01 plus 3.03. That's 17.04 grams per mole. So we have 250 kilograms of ammonia. That's 250 times 10 to the 3 grams. We need to turn that into moles of ammonia. So 1 mole up top, 17.04 grams on the bottom. This is just a grams to moles conversion. And then we'll do the gas stuff after we're in moles. So 250 times 10 to the 3 divided by 17.04 gives me a very large number, 14,671.36 moles of ammonia, NH3. So now we can use our mole ratio, because we have a number in moles, and we'll get our moles of hydrogen gas. So 14671.36 mole of ammonia. We use our mole ratio. Remember, wanted, that's what the question is asking you about, goes on top. And what you know about what you've been given in the question goes on the bottom. So 3H2s divided by 2 NH3s. So let's see, times 3 over 2. That gives me 22,007 moles of hydrogen. Now we just have to turn it into liters. So we will use nRT over P. Just like before, we've been given moles of a chemical and we're turning it into liters at a specific pressure and temperature. So here is my N with the unit, moles. We use R, that's 8.314 kilopascal liters per mole K, mole degree Kelvin. T goes on top, so 1400 Kelvin, that's pretty toasty. And then our pressure goes on the bottom, 2300 kilopascals. And we are allowed to do some crossing out. Moles is gone, kPa is gone, Kelvin is gone. Hey, look, the only unit is liters. How many liters? That guides us to the answer. It's great. So liters of H2. And now we just do the math. So 22,007 times 8.314 times 1400 divided by 2300. And we only have 4 sig digs, which means I have to turn this into scientific notation because my number is actually 111,370 liters. I guess 0.9, but that's not going to be there. So we need to turn this into sig digs. Then that's going to be it for this question. So I have 3 sig digs, which means I am going to look at these 3 significant digits, 111. So I go 1.11. Do I change that 1 into a 2? No, I do not round up because that's a 3. So I go 1.11 times 10 to the something liters of H2. So here's where my 1 is in the or my decimal is in the answer. So I just have to walk it. I have to walk the decimal in purple all the way to where the decimal in green is. So 1, 2, 3, 4, 5. So 1.11 times 10 to the power of 5 liters of H2. So these questions are not super difficult, provided you keep track of your units. But again, you wowed me during the gas laws unit as far as your ideal gas law and your other combined gas law moves. So you guys are in good shape. So I hope that helps you out. And the last kind of stoichiometry is solution stoichiometry, which is just using concentrations, which we learned in chapter or unit C. So, hope that helps.